a wee bit more, get into their definitions, their symbols, what they're measured in, and how they're measured. So just that. Show you a wee video, some PowerPoint slides, and a couple of websites that should help you get familiar with circuits and how they're made. So, first thing I want to recap is what's meant by current. Okay, so on my first page here, though, I don't know if you recognise these symbols. Those of you who have done the last homework, this is the symbol for a cell. So a cell to on its own is just a single cell. So we have a positive terminal or positive end of the cell and negative end of the cell. So we've got our positive and negatively charged parts, and that's what causes this drive for the current to get around the circuit. Okay, so that's providing the voltage, but I'll get into what current and voltage are a wee bit more in a minute, and also explain what these symbols are. So, current. Like I said, you've already come across this. A current is a flow of electrons. They flow around our circuit, through the wires, through the components. They already exist in the wires and in the components. The electrons are everywhere. But if you have your power supply, so your battery or your cell, to provide the energy, then you're going to have this flow of electrons, which is what we're calling the current. Remember, electrons carry charge. Charge is measured in coulombs. The charge in an electron is about 1.6 times 10 to the minus 19 coulombs. And that's in your data books as well, if you ever need it, when you're doing some questions on this. So it's just a wee animation to show that our electrons are going from the negative to the positive side of the cell. And we've got a complete path here, so we're able to get this flow of electrons, so this current. Just briefly, don't get hung up on the direction of the current. So here we're showing that it's going from the negative sides, makes sense, electrons are negatively charged, to the positives. But if you ever see diagrams with arrows pointing the other way, or if I'm talking about it and I seem to be going in the other direction to what you're thinking, then for the components and the circuits that we're talking about, it doesn't actually make a difference. If we're saying the electrons are in the wire anyway, and all you're doing is providing them with energy, then it's not going to matter which direction they're going in for things like light bulbs and giving those electrons the energy to change from electrical energy into light and heat energy. So don't get too hung up on that just now. We're going to get into that a lot later on in the course. Okay, but electrons are negatively charged. They are going to go from the negative terminal to the positive terminal. Okay, voltage. So our definition of voltage is the energy given by the cell, to each coulomb of charge. So that's what's providing your push, that's what's providing your drive for the electrons, so for your current. So the bigger the voltage, the bigger the push, and the bigger the current's going to be. Okay, it's also called potential difference. So I just want to make a quick analogy between voltage and electrical potential difference and gravitational potential difference. This is in the National 5 course as well, but no, you've not done that yet. You'll have done a little bit of it in first year though, so you will know that gravitational potential energy is when you lift an object to a height. So it depends on the mass of the object, the gravitational field strength of the planet, because that's the pull that's attracting it back down to the Earth, and the height that I lift it. So if I lift my pen and lift my glasses case, then glasses case is going to have more gravitational potential energy because it's a bigger mass. I had to put in more energy to lift it to that height. So cells are kind of similar. We don't really need to get into how they're created, kind of chemical reactions involved, but we've got one side being positive and one side being negative. That's created this difference, this potential difference, because we've got a drive to get from one side to the other, the same as the pen has got this drive to get back to the earth. Okay, the negative side being attracted towards the positive side. So it's called potential difference, similar to how this is a difference in gravitational potential energy. We've got a difference in electrical potential energy. Okay, so we've got a circuit here, pretty basic circuit, and kind of drawings of the components in the circuit. So I just want to show you this, show you what the proper kind of circuit symbols for these components are, and show you how you can create some circuits on a website called FIT. I'll show you in a wee second. So here we've got our cell, a switch and a lamp, it's just your light bulb, and connected with wires. It's just saying the components connected with metal connecting wires needs to conduct electricity to allow this flow of electrons to go around the complete circuit. Okay, so what the switch is doing here, you have the option to have the switch open or have the switch closed. And if the switch is open, there's going to be a gap in your circuit, so there's not going to be this flow of electrons. Remember I said there's electrons everywhere to begin with. There's electrons in the wires, electrons in the components, and you're just providing all of them with energy. If there's a gap anywhere in the circuit, there isn't going to be any current flowing at any point. So think the traffic jam analogy, cars all backed up. If no car, like all cars need to be able to move at the same time. It's not like what you might get kind of tricked into thinking at first is that the negative end of the battery holds this massive store of electrons, then they go around the circuit. So by that thinking, right, the electrons should be able to get through here fine, and then it's only when they get to the switch that there's a gap and they can't go any further. But it's not like that because the electrons are there to begin with. So if no electrons are able to flow, then there's going to be no current at any point anywhere in the circuit. If there is the switch open and there's that gap, that gets called an open circuit and there's no current at all. If the switch is closed, then we will have a current able to flow. So these are the circuit symbols for these components. Here's our cell, the positive terminal, the negative terminal. It's just showing wires. It's just making it a bit simpler, kind of laying it out like this. This bend doesn't really mean anything. Obviously, in reality, your wires are all kind of bent and stuff anyway. This is just a continuous bit of wire. We've got our lamp, another continuous bit of wire. This would be an open switch because you can see the gap. To draw it closed, you would just draw the line going straight up to that connection. More wire to the negative terminal of the battery. So there are some symbols that would be useful for you to remember. Cell, lamp, switch, and just straight lines for wires. Okay, some other symbols. We've got a battery. So a battery is just two or more cells. An ammeter, you've come across that already. An ammeter measures current. Current's measured in amps, but it's not called an amp meter, so just watch out for that. It's an ammeter, not an amp meter. And voltmeter, I'm sure you can guess, measures voltage, which is measured in volts. So battery, I just want to point out, actually, this battery is a specific battery that's made up of two cells. You see how that just looks like the symbol from the cell from earlier, the long line and the short line, and there's another one next to it. So from that, say we knew that the voltage supplied by one cell was 3 volts. Two cells connected like that would just provide a voltage of 6 volts, 3 from each cell. But some symbols for batteries, I'll just show you a couple others, aren't always composed of two cells. So if I just go on to Google for a wee second, and you can do this too if you like. If I search, come on. Oh, technology. So I'm just going to search battery circuit symbols, if it lets me. Because I was impatient. I've got too many tabs. Okay, battery. Circuit symbol. And we'll go to images once this loads up. You've probably beat me to it if you're doing the same. And then you'll see pretty similar images, but a couple of slight differences between them, so I just thought it would be worth pointing out. So this is like the one that we just had. It's got the long line, short line, long line, short line. So that's a cell and another cell. It's showing the positive and negative sides of the battery. So again, if we knew that each cell provided a certain voltage, then two cells together would provide double that voltage. This is just a single cell. We've got two cells here again, but the difference between this one and this one is the direction of the, like, this one's starting positive, negative from your cells. This is going the other way, so it's starting with the small lines and then going on to the big lines. So it'll be the opposite way around. Instead of positive and negative, this would be negative and positive. But like I said before, for our components, that's not going to affect our light bulbs lighting and things like that. Same idea here, just drawn up and down the way. This symbol here, it's got a cell, then a kind of dot, dot, dot in the middle, and you see it a couple of times. That's just indicating that there could be more cells in there. So it's 2 or more cells. We don't always need to know how many cells there are. Sometimes it's useful if we know each cell is 3 volts, then we can count the cells. But sometimes we're just told the overall voltage from the battery, like this one here. We know the battery's got 9 volts. It doesn't really matter to us whether that's 3 cells of 3 volts each, or how 9 cells of 1 volt each. It's just the overall voltage provided by the battery. Okay, so just thought that was worth pointing out, difference between a cell and a battery, and the different ways that the symbol for a battery can be drawn. Other symbols, we've got an ammeter and a voltmeter. So ammeter said measure current measured in amps, voltmeter measuring voltage. Okay, ammeters a wee bit more. In school, you'll probably use something that looks very like this. It's called a multimeter because it can measure multiple things. So it's got an ammeter setting. You can get things that are more basic that are just ammeters and they would just measure current, but this has the option to measure current and other things depending on where you position this wee dial here. So electrical current measured in amps, it's connected in series. I'm going to show you what that means in a wee second. But basically, how an ammeter works is it's taking a reading of current as it's passing through it. If you think of current like a current of water, if you wanted to measure that current, you need to put something within the current of water to take a reading of the water as it passes. So ammeters are pretty similar to that. We have to put our ammeter within our circuit, not really doing anything apart from just taking a reading. Shouldn't be affecting our current, it's just be taking a reading of it as it passes through, taking a measurement of what's going on in the circuit, what's the current. Voltmeters are a wee bit different because voltage isn't a thing in the same way as current. Current is this flow of charges. Voltage is a measure of the energy. Remember, a bit like the potential energy. So we've got a measurement of, at one point, a measurement of another point, and then we're looking at the potential difference. So voltmeters need to be connected a wee bit differently. We say they're connected in parallel, and I shall show you what that means. So back into the internet for the last time, if you can search PhET, that's what I started doing here, so let's go back. So PHET, and it's the first website. You can either click on physics here, or you can just go into the website and click physics once you're on the website. As you can see, you can use it for other subjects too, some chemistry, biology. It's just got kind of simulations for experiments that you maybe can't do at home while we're not able to get into school. So if we go into physics, we've got kind of subtopics down here, so like electricity, and we want a circuit construction. There we go, so virtual lab, and there's this one here. They're quite similar. I think this one allows a couple more things. You see there's more options down the right-hand side. For what we're doing, it doesn't actually matter which one you click. This may take a wee while. Things are being slow. Oh, not too bad. So if you click play, and then you should just be able to have a play about. So if you want more time, or if you think I'm going too fast, remember you can just pause the video, obviously, and then you can try and catch up with circuits that I'm creating. Or if I'm going too slowly, then you can change things in your circuit and see how current is affected. Seeing if current still flows or stops flowing. So, can make wee circuits just by dragging things on from the left-hand side. So I've got a battery and wires. A wee bit wire each side, and then I can add some components. So I can add this component and add a light bulb wherever I want. I could put it up here just to think it looks a wee bit nicer. I'm going to put it at the bottom. And a switch. I can put my switch before or after. Doesn't matter, this kind of car analogy, it can't be a gap anywhere in the circuit. But if you want to do it differently from me, you can put the switch on the right-hand side and just kind of prove to yourself that it doesn't make a difference. Then I'm going to connect some wires. So just by dragging it, make sure you hit the connections at either side of the components. Here too. And I could just go from this light bulb right up to the top, but I think it looks a wee bit neater if So our circuits normally get drawn in this kind of rectangular shape, and it generally just makes it a bit easier to follow what we've got in our circuit. Okay, so I've got a switch, got my lamp, got my energy source. You can see as well, this is something that you can't see in reality if we're doing it in classroom, but these wee circles are to symbolise the electrons. And you can see that they're in the wires, they're in the components. So when I click on this switch to close it, I'll have this complete path, and you'll see that they all start moving simultaneously, and our light's going to light. So if it didn't matter then where you had your switch in this circuit. Okay, so that's our basic circuit. You can do things if you like open it up, add another light bulb, see how that affects things that are going on in our circuit. The last thing I want to show you today is how you connect an ammeter and a voltmeter. So over to the right hand side, I have an ammeter. So remember, ammeters measure current measured in amps, and current is this flow of charges carried by these electrons that are going around our circuit. So to take that reading, it needs to be within our circuit, and that's what we mean when we're saying in series. It needs to be kind of embedded in this loop. Doesn't actually matter where I put it, because if you look, you can see the current is the same at every point in this series circuit. So I can just open a circuit at any point and put in my ammeter. To do that, you just click on the join in circle there and click on the pair of scissors. I'm going to open it up, give myself a bit of space, and it should be able to stick in the ammeter. Okay, so I've got a complete path. So the ammeter is still just working like a piece of wire. It's still letting the current go through. It's just going to take a reading of the current as it passes it, just like standing in the river. So it's telling me the current is 0.9 amps. So if you want now, you could pause the video, try and put your ammeter in different positions, see that you're getting 0.9 amps wherever it's connected. Okay, voltmeters work a wee bit differently, because like I said before, nothing's needing to pass through it. It's not taking a reading of that flow, it's not taking a reading of the current, it's taking a measurement of the potential difference in electrical energy at those points. So if I connect my voltmeter, I connect it out with the circuit, and as we're saying, in parallel with our component. So just place on top of the circles, and I should have a voltage reading, which is 9.00 volts. So we've got 9 volts across this light bulb. So just be careful when you're talking about it as well. We say that current flows through. Voltage doesn't go through, because voltage just doesn't flow. Voltage isn't the same as current in that way. We have the voltage across a component. If I take a reading from here, I still have 9 volts. Because remember, voltage is like the energy that's given to those charges. And we're not really needing much energy for the electrons to flow through this piece of wire. The main energy is going to be within our light bulb, changing this electrical energy into light energy. So actually, I can continue to extend all the way around our circuit, and the voltage across our battery will also be 9 volts. Okay, next video, we're going to add more components, add more light bulbs, and see how does that affect the current, how does that affect the voltage across the battery, across a single light bulb, across both light bulbs together. Are there any other ways that we can connect the light bulbs? They need to be next to each other. What if we spread them apart a wee bit? Or is there anything else that we could do by adding more wires as well to connect the light bulbs differently? So that's what I'm going to get into next time with series and parallel circuits. Really quick recap today, mainly to get away from it are current measured in amps. It's our flow of charges, flow of electrons around the circuit, measured with an ammeter, which needs to be embedded in series within our circuit. Voltage is the energy given to each coulombs of charge. It's measured in volts and measured with a voltmeter, which is connected in parallel, so that's across the component the way I've got it there. So if you want just now, you can have a wee play about, obviously, with this website and get used to how you can connect things differently. Maybe click on some more buttons down here to see what they do. It's giving us some values. Don't worry about that one, we've not talked about that symbol yet. And you can also change from, well, actually that's one thing to point out just before I finish up. This has got the kind of drawings of a light bulb, but like I was talking about earlier, you can change to the circuit symbols. One thing to watch out for with this website, because it's American though, some of the symbols look a bit different to what you're used to. So that's saying that's a symbol for a light bulb. It's not a symbol that we would use. We'd use the circle with the cross in the middle. Same when we get to resistors, they're slightly different. But it's still a really useful website and being able to make up your own circuits. Okay, so hope that was useful, and I will see you soon for the next video on what happens when we connect more light bulbs and more components in here. Okay, bye bye.